is going. It's propelling to the live streaming.
Thank you.
I'm posting on chat the link of YouTube. I put for everyone.
In reality, if someone wants to share this link, I suppose that you can take the also the link or on the chat or clicking on the a small panel that you find on the left upper part of the screen, and where it's written live on YouTube, and you can copy there from there. There's a small arrow, and you can copy from there the link. Can I ask Gloria if you could check if it's working?
I see also Erica. Good morning, Erica. Yeah, on the microphone.
Hello, everyone.
Hi, Erica.
Hi.
Nice to see you.
Hello, Erica.
Hi, guys.
Francesco, do you hear me?
Yes, Roberto, I can hear you. I cannot see you. Maybe you are in the...
You see perhaps the screen of my...
Yes, the TV.
Yes, because I am not able to switch the camera.
Okay.
I have to do so. Here I am.
Okay. How are you, Roberto?
But I have to hear this time.
Okay.
Ah, eccola.
Professor Majewski, stavo giusto chiamando al telefono, come ero io, sì. Invece ho visto che si è collegato adesso.
Sono qua, sono qua.
Good morning.
È qui da prima di te, Andrea.
Ah, ok, non l'avevo visto.
Un buon quarto d'ora, direi.
Andrea, we already checked that all the speakers of your session are connected.
Ah, okay.
Online.
Thank you, Stefano.
2 coffees.
Only two? Only two, Stefano?
Yeah.
It's better one per each speech.
Pronto? Si vede che il momento non importa, va bene così. Dov'è?
Maybe we can say that if the actual attendees, and then we will repeat it, of course, wants to propose some questions for the also during the speeches of the speakers, keynote speakers and regular speakers, you can put it on chat, and it will be someone that collect the questions. We are not sure that all the questions could be done because of time, strict time that we have, but we will try to do our best.
Good morning, Professor Lazzaro.
Good morning, Carlos. Nice to see you.
Good morning. Thank you for the invitation. And
You're
good
very welcome.
best success in the meeting.
And thank you for attending.
C'è. C'è qualcuno che sta facendo una conferenza in questo momento? O no? State aspettando?
Aspettiamo che si fa ora.
Ah,
Siamo 2 minuti.
2 minuti e iniziamo.
Professor Maiovieci, colgo l'occasione per ringraziarla ancora a nome di tutti del materiale che ci ha
ecco. Sì, perché alla fine quello che rimane è più il materiale. Quando queste conferenze che durano 20 minuti, tu devi solo fare una sintesi, ma poi la gente, come dire, entra dentro l'argomento guardando qualcosa di scritto normalmente. Lo dico. Adesso ormai le conferenze sono da 15 minuti, è evidente che se uno deve spiegare tutto l'escursus storico per arrivare a qualche ricerca, a qualche progetto, qualche cosa, ci vuole molto di più.
Grazie
ecco
infinite.
perché vi ho mandato un po' di materiale, insomma, almeno quello. Andate a quel convegno a Londra, a Guildford?
Sì, l'idea è di andare.
Stefano, maybe we can start.
Yes, we can.
Okay, it's my time to welcome everyone and connected here for the first Italian workshop on shells and spatial structures, IWSS2020. I can say that I'm really excited about two great first times, in my view. The first time that I'm a main co-organizer of an event like this, and the second first time is that it's the first time that I organizing an event online. And so, okay. First of all, I really need to thank my friends and main co-organizers of this event, Amedeo Manuel Lubertetto from Politecnico di Torino, Andrea Micheletti from University of Rome Tor Vergata, and Francesco Marmo from University Federico II of Naples, for sharing with me, but I can say all together, this maybe small, but for us, very significant adventure. And the starting point of this idea of organizing the IWSS goes back maybe 2 years ago, when we some of us firstly met during the IASS conference, the conference of the International Association of Shell and Spatial Structures in Boston. And then last year again in Barcelona, and where we discovered that we have great common interest for shells, spatial structures, and also we discovered that we are working on both topics that are of interest for engineering and architecture, for modeling and simulation, for the history and the design of beautiful and complex structures, like the one that we will discuss during these workshops. The second great thanks goes to all the keynote speakers that kindly accept our invitation. And we really hope that everyone in this workshop now will enjoy the talk. And I put here on the right side of the screen, you don't need to try to read what is there, but this is something that summarizes all the contribution that we will have. So with this, I want to thank all the authors that have been time and have been able to accept our invitation to participate in this workshop, and mostly in this particular moment where it seems that we are much more busy than in other periods, in other normal periods, and it seems that we are immersed in a strange new life forced by this COVID outbreak. But what we are trying to do here also to transform this initial crisis is hopefully a new opportunity. And clearly this workshop is inspired to the International Association for Shell and Spatial Structures themes, but also because in Italy there's a strong history about strength of material, solid mechanics, and structural mechanics. We also are very near to these teams, and in fact we received for this workshop, and we are very grateful also to these two associations, two important endorsements for the ISS and for the Cisco, that is the Italian Society of Solid and Structural mechanics. And we will host tomorrow two important communication from them, from Professor Carlos Lazaro, Vice President of the IWSS, and Professor Luciano Rosati, Vice President of the Cisco. So with this, I think that now you can relax, try to enjoy the workshop, and maybe fitting the right outfit, dressing the right outfit for an online conference. And last but not least, remember that the workshop will not finish with the workshop because we want to try to make a final toast online, more informal way where we can share drink and ideas and feedbacks and everything. So now I leave the screen to my colleague Amedeo Manuello, and please, Amedeo.
Well, thank you so much, Stefano, for introducing the birth of our ideas and our goals so clearly. Like the best adventure stories that normally start with one upon a time in a dark period, also in our case, the way of IWSS began in a very difficult moment, I think. A period of crisis for our country and for the whole world itself. The COVID pandemic disease, of course. Personally, I still remember the first online connection during the early lockdown phase. It was not clear how long the silence around us would be lasted. At that day, it seemed inevitable to cancel completely the meetings. Unexpectedly, we decided to face the situation, and we thought that the best way to make ourselves useful in our society was to continue to do our duty in the best way. We have rethought the entire workshop through an online tool, interpreting the workshop by this new idea. We tried to bear the many negative sides of the situation through the possibility of developing the only true positive condition, the only one. The possibility to increase the inclusiveness. For this reason, our meetings have been designed to encourage as much as possible the connection between the participant via the Zoom platform and the entire workshop. It's shared live by a YouTube streaming. This leads us to move the workshop to the not only Italian workshop on shell and spatial structure, and is giving the possibility to reach a big number of interested people. In this slide, I decided to collect some images to tell you the location where the workshop was designed originally. This location was also chosen to immerse the participant in a very particular architectural context. The unique combination of the 17th century architecture of the Valentino Castle and the structures of Pierluigi Nervi and Riccardo Morandi, of course, built starting from 1950. Please, Stefano, if you can start the video. Okay. This kind of architecture are the natural environment for IWSS. In this video, we show you the seat of the Valentino Castle. The castle today is the home to the Faculty of Architecture of the city. The building was included in the list of UNESCO World Heritage Site in 1997. Just ahead a short distance, you can see the Riccardo Morandi's pavilion. Pavilion 5 was built in an underground hall and consists of a vault without intermediate support made of thin precessed concrete structures. Finally, we come to the main structure of center of Torino Esposizioni, built in the 50s by Pierluigi Nervi, and showing one of the most important architecture in the city. This structure, established by the wonderful pavilion B and C, are the subject of a specific virtual tour that you can find on the website and that I invite you to watch. Perfect. Before giving the floor to my colleague and friend, I would like to show you an additional feature of the workshop, starting from the assumption that meetings very often represent an actual opportunity to enrich proper work and research. We thought to receive some of the works through the publication of a special issue devoted to the themes discussed in our sessions. In the journal Current Layer Structures, the publication of these works will be obviously free of charge. In this regard, I would like to thank the editor-in-chief, Professor Francesco Tornabene, and the publisher of the journal for their great willingness to publish the works of the workshop. The time is right now to throw the ball to my colleague and friend, Francesco Marmo.
Good morning, everyone, and I wish to welcome every one of you within the IWSS 2020. So let me talk about the numbers of the IWSS. In January, we were planning this workshop without any clue on what would happen in the next months. We were imagining a small workshop with less than 20 contributions and just 4 invited keynote lecturers. The lockdown forced us to move the workshop online, and this gave us the opportunity to enlarge the size of the event. With our great surprise, the number of contributions has more than doubled with respect to our expectations. Also, it has been much easier for us to invite prominent personalities involved in the design of shell and spatial structures from all over the world. We have authors from almost every continent. Of course, we miss Africa and Antarctica. Perhaps we have no chance with Antarctica, but we can certainly work harder to include Africa in the next future. We also had the idea of inviting authors to contribute both with abstract and additional preview material in the form of short papers, commented slides, or videos, in order to short the online session without limiting the amount of information they decide to share with the audience. This preview material is now collected in a specific page of our website. I invite all of you to take a look at these files. Next slide, thank you. We were also planning to set up a small exhibition within the Valentino Castle. Of course, all this exhibition has moved online, thus becoming a virtual exhibition. We have a specific page on the workshop website devoted to the virtual exhibition, together with the virtual tour already mentioned by Amedeo. In this exhibition, you can find an asset tensegrity structure, which is composed of multiple concentric layers of tensegrity elements. The beautiful pavilion composed of spiral timber elements. Actually, this is one of the prides of the Italian community that works on the themes of the shell and spatial structures, since a similar structure was awarded during the IWSS conference in Barcelona last year. In our virtual tour, you can also find a beautiful series of bamboo structures. Bamboo is the most carbon absorbing plant in the world, and it represents a promising challenge for the future of shell and spatial structures. Of course, I will not tell anything more about the structure of our virtual exhibitions, since they can be presented in a much better way from the authors during the sessions of our workshop. Next slide. So the technical program, the entire program of the workshop includes many interesting lectures regarding the analysis, designs, and construction of shell and spatial structures. We set up 8 sessions of about 90 minutes each, 2 in the morning and 2 in the afternoon. Each session will start with a keynote lecture and will continue with a variable number of regular talks. The only exception is the session on Friday evening, the last session, that will have a keynote lecture at the end. Breaks between sessions will be used to gather all lectures for the next section and to allow the chairman to verify that all speakers are ready to talk. So I invite all speakers to connect and talk to the chairman during these breaks. Okay, so the time is gone, my slide is over, and Andrea Micheletti has something to say more.
Thank you, Francesco. These are the times of our keynote lectures. I thank again all the person who accepted our invitation. On the left, you have today's lecturers, and on the right, tomorrow's ones. These are Central European Summertime Hours. Please take note of the times to not to miss them. So today, as you might know already, the first lecturer is Professor Massimo Majewski, and he will talk about upgrading the spoked wheel concept and other things maybe. This morning second session will start with Professor Maurizio Brocato's presentation about stereoplexy. Then in the afternoon, we will listen to Professor Sigrid Adriansen's talk about a different perspective on shells, and it's actually morning for her. And the last session for today, we start with Professor Nikos Lagaros talking about topology optimization driven conceptual design of structures. These are all super interesting talks, like those we will have tomorrow. And tomorrow morning, we start with Professor Tullia Iori telling us the story of 3 engineers of the past and what history can teach us in times of emergency. The second morning session, we start with architect Mauricio Cardenas presenting his very nice projects with bamboo and what he can do with it, with this wonderful material. Then tomorrow's afternoon, we continue starting with Professor Giuseppe Marano, presenting the state-of-the-art and future challenges in evolutive algorithms for structural optimization. And at the end of last session of this workshop, we will have Professor Alberto Carpinteri, who will talk about funicularity in elastic domes, coupled effect of shape and thickness. We are grateful to have you all here, keynotes, lecturers, co-authors, and listeners. Thank you very much. So in the next slide, we recall some quick instruction for enjoy this online meeting. So first, of course, it's better if you choose a quiet environment, and you can ask to talk about, you can, by using the chat. So to open it, you just need to click here, and then you can type your request to speak, and the chairman will invite you to talk. And then please remember to mute your microphone if you are not talking, and unmute it if you are when you're going to talk, and you can use the button on the lower left corner of your screen. And of course, you need to share your screen when presenting using this big button in the middle of the bottom of the screen. Once you click it, you can select the top left icon to share your desktop, or select the, say, PowerPoint window to share it. So we can finally start with the presentations. I recall that the keynotes have 50 minutes plus 5 minutes of question and answers, and that regular speakers will have just 5 minutes plus 5 minutes for questions. So now I'm honored to very much to chair the first session of the workshop, and even more to introduce its keynote speaker, Professor Massimo Majewski. With his Office for Structural Engineering in Bologna, he created a remarkable number of projects, and among them we have the membrane covering of Piazza Italia, of the Fair District in Milan, the roof of Athens Indoor Stadium, the Olympic Stadium in Rome, and the Delle Alpi Stadium in Turin. Having designed more than 200 constructions, both in Italy and abroad, Majewski earned a great deal of expertise, which represents the foundation of Majewski's experience-based synthetic conceptual design approach, designing wide-span enclosures from conceptual to working design phases entails facing particularly complex structural problems due to the scale effect of the loads involved. So when I was a student, I was reading a paper about the Olympic Stadium describing the structure and a bit of the design principles. Then I realized that while I knew the stadium, because I was going in there to watch soccer matches. At the same, I never thought about how it stands up. And while reading this paper, I remember I was very impressed to mention one thing, for example, by the sheer size of the structural elements. Also, as we mentioned before, I want to thank once again Professor Majowiecki for providing the very nice material, a rich document you will find on the website. And now I have some questions which I prepared to, which we prepared to have this time with him. Professor, so first thing I will share the screen and show the one of the documents you provided. This is about the Olympic Stadium and the Yaoundé Stadium in Africa. So I would like to ask, what are the differences in cost and structural performances between these two stadiums?
Yeah. Yes, well, thank you for the invitation. Good morning to everybody. And the paper that you are looking in this moment in the screen, I took the opportunity to make a parallel in time, about 30 years difference between the Olympic Stadium and the Yaoundé Stadium in Cameroon. But I took the opportunity also to present in this first conference, Italian conference on shell structure, because the Olympic Stadium, maybe nobody knows, that was the first of the family of the wide span spoke wheel roof covering stadium in the world. And then I took the opportunity to present them in Boston. And I also appreciate very much to be awarded with the first prize of this paper in Boston. Now I like to represent here in Italy, because this is an Italian construction that maybe was the starting point for many other construction around the world. And then I was it, but at that time I have a lot of really preoccupation, because at that time I was very preoccupied about the dynamic behavior, and maybe this is the first time that we make a roof of more than 300 meters with a hole in the middle. What happened? Maybe it will happen something like Tacoma Bridge, etc., etc. I don't know where I found the courage at that time to do that, and it seems to me that is another one, not me, because then this is uncorrelated in time. But anyway, the spoke wheel concept like that was very difficult, because as you see, was supported vertically only by 12 columns. Really a lot of particular problems in such a construction, but we succeeded to do that in 16 months. And still now I don't understand how we succeed to do that. Anyway, for Yaoundé Stadium, what is the new proposal? The new proposal is that we have a different way of erection, because the so-called big lift procedure for the Olympic Stadium was much more simplified, using, the bearing cable. You see the radial carrying cables there, the red one, the violet one, and this is what we need, because the only thing that we need to get the equilibrium is the angle of this carrying cable that give us give us the possibility to carry the weight of the secondary part that up there, that is an hybrid steel structure that is supported by the flying mast, the green flying mast. Then that's all we need, and therefore we simplify the system for direction, because what on the right you see the panel, the panel that has been erected all together with the membranes and so on, and then was much more easy, economic, and time consuming in the building site. Also, there is a very good safety, because you see the carrying cable, and the secondary part that you see is an arch of 3 hinges. Then it's very adaptable to any kind of tolerance in the lifting end of the ground. Then, what was possible to do? That was possible because we adopted the so-called tie-down system. That the tie-down, it means that if for instance, I place the panel on the tension ring, there was displacements of maybe 1 meter and more. And then in order to have a very easy erection, the tie-down system, I think there is a figure there for that, maybe. Yes, you see, maybe.
The analysis.
Yes, okay, on the left, yes, the last one on the left. You see an installation of a tie-down cable. Then the tie-down cables have an initial force that is more or less the dead weight, the permanent loads of the secondary structure. Then the support is in the right place, and there is not movable, because the tie-down is bigger than the permanent loads. And then with this easy way of construction, we obtain a success in time and in cost. That's all for this.
Thank you. So let me just quickly go to the second question. This is maybe something more personal, probably. Can you tell us something about your contacts during your career with Frei Otto?
Frei Otto, more or less, I was a student at that time, because I had the opportunity to meet Frei Otto in a conference in Stuttgart, and at that time I was preparing a doctoral thesis about lightweight structures, and I have a photo of the Olympic 72 Olympic Games, and then I didn't know that at that time he was removed from the design team. And then I presented my photo like a student, and he signed, but I say, I will sign reversed, because I don't like anymore. This was my only contact with Frei Otto. A very nice person, but I didn't know that at that time was a problem, because they spend a lot of time, because was the first time Frei Otto innovate the state-of-the-art on lightweight structure, but the construction had a lot of spend a lot of time in the design, and then he was removed, and Venetian partner was awarded the design. A special problem. You remember this for me.
Okay. So I thank you for telling us this story. So now I have another. The next one is does lightness of a tensile structure always correspond to low cost of construction and maintenance? This is
not at all. But sometimes yes, especially for very wide span enclosures. This is around 40 meter span. I think a lightweight structure is very convenient for both for cost, but for the safety and the reliability correlated to the cost.
oh, okay. And then here is another question. What can be the impact of structural details on the conceptual design of a lightweight structure?
This is a very important thing because the detailed design in a structure like this that is from the safety point of view a chain, then is you cannot have a ring that is a weak part of the safety chain. And because the lightweight structure, more of the lightweight structure are hypostatic, then they have no, redistribution of the forces if some element have a failure. Then the robustness of the lightweight structures must be obtained by the system, but not by the detail. Then the detail is very important to avoid initial collapse, and the system must short-circuit the progressive collapse. And that's why I think is very important. And then for the lightweight structure, I think also is a big part of the architecture of the system.
Definitely. Okay, so I have more. This is maybe again something a little bit more personal. Is there a structure you realized that gave you a hard time, but also great satisfaction? I'm sure the Olympic Stadium was one of these. But...
Yes, I think the Olympic Stadium remained my because it was the design that involved me in a very deep sense between the correlation between the knowledge base that I had at that time and the courage to go ahead with something really new, very big, and at that time, wind engineering was a very lack of knowledge, and then this was the opening session of wind engineering in Italy, and I have a very good technical adventure with Western Ontario University, especially with Professor Vickery, that is a very big guy. And then he said me, we have no experience in subhorizontal structures, and then we have to gain knowledge on that, and together he gave me a little bit of confidence about something that I will always remember, the aerodynamic damping. He said, I think you will be helped by the air, the moving air.
I see.
And then the stability of the dynamic stability, okay, this is design adventures.
Okay, okay, very good. The next one is what is in your opinion the peculiarity of the Italian school in lightweight structure in the last 40 years?
You see, I remember when and I'm speaking about the 1969, when I approached to have a doctoral thesis about that. Yeah, I was in a place in Italy dominated by the concrete structure. Even the steel teaching, steel structure teaching were not open at that time. Even in Bologna, there were only few teachings, maybe in Torino, in Milano, but this was a country dominated by the concrete. Well, we pass from the heredity of Nervi, Morandi, Musmeci, and Musmeci at the last time he tried to initiate, the school of the minimal surfaces, then the bubble surfaces, the membrane, but he have done a membrane structure. You know very well the famous bridge of Sergio Musmeci, and that is a reversed. Not the temptation to do a membrane, but is a membrane under compression. Because was reversed in shape and something like was done at that time also in Spain. Somebody like the architect Gaudí, he made trying to make something according to the minimal surfaces. Then the membrane concept that was initiated at that time. And from Sergio Musmeci, yes, something has been done, and I hope you will continue it. You are the younger people now. I'm very satisfied that in Italy we can follow and open and continues the lightweight structure concept.
Yeah, let's hope so. Yes. So that was the last question, and we are all very thankful, and especially thankful for this nice chat we had this morning, and it's very instructive for all of us to listen. And
okay, thank you very much. Thank you very much.
So
maybe we can ask if there's one question from the
there is time for one more question. Yes, if somebody has one quick question.
Sure.
Yes, Mauricio Cardenas. You can switch your microphone.
Can you hear me?
Yes.
Yes.
Massimo, I would like to know which is your favorite classic structure from classic architecture from the past.
Ah, from the past.
Yes. And why?
And why? Because when I was in the Venice University, yes, I really appreciate the cupolas and because I say, well, it's incredible, and these people that can do that without any computer, and then cutting a stone that have three meanings. This is a stone that is engineering static, architectural for the shape and the mystic of the cupola, etc., and also a sculpture because the stones were cut inside like a statue, etc., etc. And these people have the possibility to cut perfectly one by one and then putting all together and realizing and realizing, you know, these master builders. And I have in some of my conference, I also show a photo, a statue of that time, because a master builder make his face. He left the sign by a statue of himself. You know, he's in 1379, and then I was really impressed about this guy and all the other guys that have done at that time. That now, from here, we are in the other side. And then in the structure, we have, like in philosophy, yin, yang.
Yes.
Yes.
And then, but everything is in the middle. In the middle, we have something that we don't understand. That is the plate, the beam. That is something completely hybrid, but also exists. In reality, it's only the deformation of the two, the yin-yang, deformation, and then it's something that we call a plate or a beam or something like that. Okay.
Okay.
Thank you.
Time is up. Thank you again, Professor, for staying with us, and I hope you will keep us company in for.
Thank you very much, Professor.
Thank you, everybody. Thank you, and bye.
So yes, we need to rush. I apologize for this is the format of this workshop. We need to. It's a sequence of short, very short. Sorry. Okay, so we have the next.
What about the coffee break?
The coffee break will be at 10:50. So we have 4 talks now, 4 regular contribution, and the first one is by Enrico Ossola and his co-authors about geodesic domes for planetary exploration. And I would like, yes, the presentation is already up.
Yes.
Please, Enrico Ossola, go ahead.
Thank you. So I'm Enrico Ossola. I'm a PhD student from Politecnico di Torino, and this research was performed in collaboration with Jet Propulsion Laboratory. The presentation is about geodesic domes for robotic planetary exploration, and in particular for exploration of extreme environments. Our research is focused on a concept for a potential lander for Venus. And actually the surface of Venus is an extreme environment because it's characterized by very high external pressure and very high temperature. About 40 years ago, Pioneer Venus and Venera probes successfully landed on the surface of Venus. And from a structural point of view, they were basically plain spherical shells. So we wanted to investigate if some internal ribbing can be helpful in withstanding the extreme loading conditions. We thought about the isogrid layout, which basically is a pattern repetition of ribs forming triangles, and it's quite common for aerospace applications, but it's almost never been used for spherical shells because it's hard and expensive to manufacture. On the other side, in architecture, isogrid hemispheres are pretty common and they're known as geodesic domes. So aim of the research was investigating the behavior of metallic geodesic domes fabricated by additive manufacturing for a potential use for planetary probes. So the problem is pretty simple. It's basically in a hemisphere subjected to uniform high external pressure, and 2 failure modes are possible: yielding or buckling. The most critical one is maybe buckling, and some analytical formulations are given in literature for estimating the buckling critical pressure, but they need to be modified by using some empirical factors, the knockdown factor KF, which somehow takes into consideration the effects of imperfections. this KF is pretty variable, and the suggested value, the recommended value for industrial application is about 30%, so it's pretty low. In stiffened shells could probably result in some more robust designs and less sensitive to imperfections. This is the isogrid layout with the main isogrid parameters. Basically with some analytical formulas, it's possible to predict the stress state of a spherical isogrid shell. And again, two failure modes are possible, yielding and buckling. However, for the buckling, the situation is a bit different in respect to the plane shells, because we can have the general instability of the whole sphere or some local failure modes which are skin buckling and rib creeping. For example, in skin buckling, when the skin is really thin, it can buckle, just one single pocket can buckle, or when the ribs are very thin and very tall, they can cripple. So the problem is finding the optimum isogrid configuration. And we started from a paper from the 70s, and we wrote MATLAB code to optimize the isogrid configuration. The optimum is assumed to be reached when the three buckling modes take place at the same time. But two questions remained open. One, will additive manufacturing actually work for thin shells? And what will be the actual behavior of isogrid hemispheres? So we decided to go testing. And so this is the path we follow. We designed 20 centimeter hemispheres with the analytical tool we wrote. Then we refined the geometry to improve the manufacturability. We performed some numerical simulations, and then we fabricated three isogrid hemispheres and one plane hemisphere made of Ti-6-4 using additive manufacturing. And finally, we tested the shells under hydrostatic external pressure, basically increasing the pressure of the chamber up to the failure of the shell. So here, for example,
you have just one more minute.
Sorry?
Just one more minute.
Oh, okay, yeah. This is one of the shell failing. Results. So the three isogrid shells fade at about the same pressure, and nonlinear simulations were found to be consistent with the experimental results. What is really interesting is taking a look to the knockdown factor. In the case of the plane shell, it's very similar to the one suggested by literature for traditionally manufactured shells. And in the case of the isogrid, the knockdown factor is 44%, so significantly higher in respect to the plane shells. This means that maybe the isogrid shells are less sensitive to imperfections in respect to the plane ones. So in conclusion, we showed that additive manufacturing is a way to fabricate shells for probes for extreme environments, and the isogrid layout can improve the mechanical behavior of these shells. Some future activities are needed to estimate the mass savings related to the adoption of this internal reading. Thank you.
Okay, thank you very much. So I will quickly ask you that a couple of things.
Yes.
One is if there are other architectures for the reinforcement. So, for example, you can consider a three-dimensional geometry for a metamaterial, or maybe a hierarchical geometry. And the second thing,
we started with this isogrid geometry because it's well known for aerospace applications, but we are thinking also about having a sort of sandwich structure with two skins and some lattice or architected material in between. But there are some problems about manufacturing because it's a bit more complex.
Yes, also I guess it's also harder to have evolutionary algorithm for optimization with respect to backlink. This is not easy.
Yeah, we didn't use any genetic or evolutionary algorithm, but just some analytical formulations because this is just a preliminary study, so we needed a fast tool to design the isobit layouts. But it's a good idea for maybe checking and validate the models.
And the last, very quickly, about corrosion, because additive manufacturing suffers from corrosion.
So actually the surface of Venus is a very corrosive environment, but some coating are possible. So we can basically coat the titanium shells with some material, some ceramic material, for example, and improve the corrosion resistance.
Okay, so thank you very much for keeping the timing. I need to switch to the next contribution.
Oh yeah, stop.
Thank you, Enrico.
Thank you.
So we will have Francesco Laccone and his co-authors talking about. He will talk about the FlexMaps 2.0, a bending active structure with optimized spiral mesostructures. And this already.
Good morning, everyone. Can you see my screen?
Yes.
Can you hear me? Yeah.
Please,
okay,
excuse me, if anybody wants to put up a request to talk, to ask a question, please do it in the chat. This is just a reminder. Please go ahead, Francesco.
Yes, thank you. So good morning. I'm going to talk about FlexMap structures, which are a particular class of bending active structures. In general, bending active are form-active shapes that are made of flat elements that are so initially flat, and they are bent in the elastic regime. The work I'm going to present builds on a computer graphics research that aims to realize small-scale objects out of flat patches like this one you see here in the video, and this approach discretizes a generic object into deformable mesostructures in the shape of a spiral. We tested this approach at the architectural scale for the first time at the IWSS2020, which took place in Barcelona last October, and we used a challenging shape of a twisted arc you're seeing in the slide. And with this result in mind, we developed an automated design methodology specific for architectural shapes. And we tested it in a demonstrator project that we realized at the School of Architecture of the University of Technology of Sydney. So I will briefly record the main steps of this methodology. So what is the concept? The object reaches its final shape once all panels or patches are individually bent and then tied together. So the panels are initially flat and then are bent by hand, and also appropriate conditions are applied. To connect the patches together, we used a key connector that has an interlocking shape, and so the pieces are locked by friction, mostly by friction, and then we use 2 bolts to avoid any other relative movement. The shape is a designer choice. There are no particular restriction on the shape, so there is no need for the shape to be funicular or to be developable, and the red frame you see on the screen is the shape we selected for our demonstrator. We quadrangulate the target shape with quads that are as regular as possible and aligned with the boundaries. So the quadrangulation is fundamental since each quad embeds one spiral. So the quad defines the size of the spiral. Then we use the FlexMaps algorithm to tune the spirals in a certain stiffness, such that at the equilibrium, they are as close as possible to the target shape. The stiffness of the spiral is governed by only 2 geometrical parameters, which are the spiral thickness and the spiral twist. And we can obtain locally different stiffness parameter only by altering the geometry. So we no need to work on the material. And also for this specific project, we decided to further constrain the parameters range in the red framed space you see in the picture. An important step we added in this method is the FEM validation. We were able to automatically produce an ANSYS solid model. In order to check the stress and the displacement field, and in general to estimate the safety level of the structure. The last step is the automatic generation of the files for the CNC machine milling. This is a short video of the assembly of the structure. It took about 3 days, manually bending one patch at a time and connecting them together. We also dedicated attention to the design of the floor, which I'm not talking about, but this is not merely aesthetic, but has also to provide resistance to the thrust force and to the bending. And just to conclude, we can state that the FlexMaps approach can be definitely used in also at the architectural scale. And this demonstrator is our validation for the method. This method is very straightforward, and the whole process from the conceptual design to the assembled structure took about 1 month. But just consider that the fabrication took about 1 working week, and there are also some design aspects that were not automated. Thank you for your attention.
Thank you very much, Francesco. I see that Amedeo Manuelo has a question. Please go ahead.
Yes, thank you very much, Mr. Chairman. Yes, I want to ask, what about the loading configuration that you used during the simulation, the numerical simulation? Which is the loading that you put into the structure, on the structure?
Yes, thank you for your question. You mean in the FEM model or during the optimization?
Okay.
Because in the FEM, during the optimization, we just compute the equilibrium of the structure under the dead load, the gravity load. And in the FEM model, we developed a 2-phase model. In the first one, the panels are bent, individually bent, starting from a flat position, which is as close as possible to the supposed target shape. In a second phase, we connected the patches together. So we applied a kind of bonding condition between the patches. We release the stress, so the stress redistributes on the surface. And then we applied gravity and other loading. In this particular case, this was an indoor installation, so we just applied gravity load and some safety load on the boundary due to impact of, in the event of the impact of people.
Yeah, thank you so much.
I don't see any other request in the chat. So Stefano Gabriele is reminding us that this is in our virtual exhibition, this contribution. And so there is time for one more question, and I would like to ask how much the construction procedure can affect the stresses in the elements.
Yeah, thank you for your question. It's actually a good question. And the construction procedure does affect the shape and the stresses on the surface. To be honest, we do not simulate the real construction phase, but we try during the assembly to keep the panels as close as possible to its final deformated shape, because it could happen that the panel could be brought in a large displacement field that is not compatible with the material limitation. So the assembly phase could be done in a very careful way.
Okay.
In the end, the stress redistributes, and luckily the shape pops out automatically.
Yeah, it would be interesting to measure, to monitor the stresses.
Yeah, actually, there are ongoing scanning on the surface, and to check
maybe
the
also
real
sensors, to place some sensors here and there. Okay, thanks a lot,
Thank you.
Francesco, for your presentation. Very nice. So I go to the next speaker. Is Milan Dragoljevich with data-driven design of deployable structures.
Thank you, Andrea. Just a second to share the screen.
Yes.
Okay, so can you see my screen and can you hear me?
Yes, it's perfect.
Okay, thank you. So my research was focused on two things. First was the research of the current case studies and current classifications of the deployable structures. And the second part was focused on trying to develop the data-driven approach for the deployable structures. As you're all mostly familiar, the two areas in which deployable structures are used the most are the events, so organization of the temporary exhibitions, concerts, etc. And the other one is emergency situations, when you also need to deploy the structure very fast. So in order to reach this point where you can deploy the structure very fast, there are a couple of requirements for the structure, like minimum self-weight, high energy efficiency in use, etc. So we try to find the data-driven approach that could pick up all these requirements and use data to apply them even more than that is currently case in structures. To start the research, we started from understanding the classifications and divisions that are existing among the deployable structures. So here you can see the timeline of the development, and you can also see that starting from 21st century, the deployable structures were examined and classified more. I mean, the first classification was in 1987, and then the next one in the 21st century. So now I focused on them, and I can maybe anticipate a bit. The focus of our interest was on scissor structures. So we tried to understand in different types of the classifications how they classify the scissor structures. So they were all here as a part of the strut structures. Then in the classification by Gantt, they were under the earth-based deployable structure. So that means they have a significant, not significant, but that the self-weight is an important part of their load. And also by Pellegrino and under the structural mechanisms. This is one of the most important classification. It is most referenced one. So Hanor and Levy used it as a part of the rigid links and skeletal structure. Korkmaz in 2004 also under the, this was the division based on the application in architecture. So it goes under the buildings with variable geometry. Schaffer and Vogt in 2010 under the rigid materials. And by Stevenson, you can see there's a whole series of different scissor structure that he examined. So here it was important for him to understand the movement of the whole structure and also of a single element. And as you can see, the scissor structures can have a different movement on large scale, while on the small scale, it's always the rotational movement. And yes, by Del Grosso and Basso, also under the rigid links, this is connected to the work of Hanner and Levy. And in the end, by Rivas and Adover, it's a type of the construction that starts from structural component, and then the whole structure is designed, let's say, down to top. So to summarize one more, so scissor structures are also interesting because they have a linear element and their self-weight and use of the material is quite efficient. So you don't have any additional elements that are not loaded. All the tubes or poles are loaded and either compressed or tangent. So that's why it was interesting to see how far can we push this utilization of the elements and of the materials. So to sum up the possibilities of the movement, so you can have a linear movement, you can have a radial, circular, etc. And in the end, we focused on the dome as a 3D structure that can cover the most of the space compared to the, let's say, vaults or some single curvature elements. And we developed this parametric 3D model in Grasshopper with two elements, a scissor system that are in fact tubes, and fabric cover that are membranes, but thin membranes. And okay, here you can see the model in whole, and here you can see the generation of the dome. So this is also controlled parametrically, diameter and frequency. Frequency is in fact the number of divisions. So let's say the design can now be guided with, can be supported by this algorithm that allows you to generate the structures almost instantly. And these are the materials that we used for our simulations. So steel Q235B and PVC extruded material as a membrane. Also initial dimensions were poles of diameter of 3 centimeters with thickness of 0.5 and membrane of thickness 0.45. But this created a problem because, as you know, for Karamba, you have two types of the algorithms that you can use for calculations. So for the membrane, we needed...
Milan, you have just 1 minute. One more minute.
Okay, I'll speed up. Okay, so for the membrane, it's important to use a large deformation algorithm, and for the poles, it is used the first order theory algorithm. And then it was challenging to find a way how to create the nodes where the load from the membrane will be transferred to the poles, but we managed to do that by using supports and understanding the load in the support points. And in the end, we tested our structure on the snow load in Milan that in the end brought a maximum displacement of 45 centimeters on 12 meters of diameter, so not so much. And we did the same thing for the poles, and then we did the same analysis for the wind load based on the Eurocode. Yeah, you can see here, it's just a displacement of small 6 centimeters. And this is, let's say, the also most important part for the decision maker. We managed to extrude the maximum bending moment at the structure that is 0.93 kilonewtons meter. It's happening in the case of the snow. And then we compared it to what the cross section of the poles can resist.
Okay,
so now,
I'm sorry, I need to cut in.
okay.
Oh, nice. This is please conclude.
Okay, so yeah, so for the further research, we will try to go more into hybrid structures and into innovative materials and try to include them in our algorithm.
Okay.
Thank you.
Thank you very much. So it's interesting because it's also connected to our first talk, and here you have also a pre-stressed structure. So the quick question is do you did some analysis taking account pre-stress and the possibility of buckling? So or you are planning to do so? Because
Yeah,
it looks very promising as a geometry. It should be quite strong as a deployable structure.
Yes, so our next, so yeah, that's connected with our further research. So including this internal loads that exist in the structure before the external load of the snow or of the wind.
You mean internal actions, right? The pre-stress.
Yes. So bending active is also one field that could be interesting considering this internal pre-stress.
Okay, and I guess also you need to do a buckling analysis. Maybe the pre-stress is too high, and then the structure suffers more. If it should be a trade-off, probably.
Yeah, of course.
Okay. Yes, there is Stefano Gabriele, and I will give one chance to Stefano Gabriele to ask a question.
Okay, thank you.
One quick question. Thank you for your presentation. Very interesting. And I think that the tension that you will have in the membrane is a very important parameter for the global stability of this kind of structures. How do you think you will control this tension in the membrane in the real construction?
Sorry, I didn't understand the tension in the membrane.
Yeah.
So how to control when you build the structure? How to impose the right pre-stress? How do you do it?
The right pre-stress. Well, I guess we will also need to develop maybe some generative algorithms, or we can in a similar way to having the table like this, understanding what is acceptable, what is not acceptable. Because I think this algorithm helps because you can generate the, let's say, the maximum that material can resist, and also compare it to the maximum that is generated in the structure. So maybe going in that direction.
Okay, I'm sorry, Amedeo, but
don't worry. Don't worry.
So 2 minutes is already a big delay.
It doesn't matter. The time is over.
Yes. So next, thank you very much, Milan, for the presentation. Next speaker is Gabriele Mirra and we talk about, and his co-author, generative models for the design of shell structure. This is the title of his presentation.
Thank you for the introduction. So this presentation is about testing generative models for the design of shell structures. My name is Gabriele Mirra, and I'm a PhD student at the University of Melbourne. So current approaches in computational design are based on the definition of a limited number of design variables, which forces the designer to focus on a well-defined class of solutions. So in this presentation, I'm going to show you a different approach based on artificial intelligence. So with AI, a computational model can learn the design variables from a dataset of design precedents and reuse such variables to construct a design space which contains a large variety of solutions. When talking about artificial intelligence, we refer to a specific class of machine learning algorithms called artificial neural networks. This can process data to extract or generate visual features. So depending on the model architecture, these models can perform different tasks. On the top, you see a typical implementation in which the model is trained to extract the visual features from a dataset of precedents and to reuse such features to classify such designs. On the bottom, we see a different implementation in which the pipeline is reversed. Here, the model is trained to expand the information, low-level information, and to generate new data samples. The differences between these two models results in either data compression or data expansion. So the model chosen for this application is called variational autoencoder. It combines both architectures to perform different tasks. The first part of the model, named encoder, learns to extract design variables from a dataset of precedents and to construct a lattice space, which is here considered as the equivalent of a design space. The second part, named decoder, learns to decompress the information contained in these variables to generate new data samples. This is an overview of the application I've developed. it starts with the development of a dataset to train the AI model. Then the AI model was trained on this dataset, and the evaluation is done by analyzing the property of the latent space. And finally, I applied this trained model to generate new designs. So the dataset was constructed through a parametric model. On the top left, you can see the design variables which were used to generate a design footprint. This was then fed into a dynamic relaxation algorithm to generate a 3D model of a potential shell structure design. Finally, all the 3D models were converted into that map, which are bidimensional representations of the points or the height of the points lying on the surface of the 3D model. And this is a format which is readable by existing neural networks architectures. In this animation, I show how this process was automated through a Grasshopper script, starting from a random combination of variables, the generation of a 3D model, and finally the conversion of the 3D model into a 2D depth map. This is the result, which is 800 3D models represented as depth maps, which are divided into 3 categories, which are shells with 2, 3, or 4 openings. After constructing the dataset, training can be done. First, you start by feeding a random batch of the dataset into the encoder and ask this part of the network to extract design variables, which are represented at the center in this diagram. Then the decoder, starting from these variables, tries to reconstruct the original input data. Over several iterations, the model is able to extract increasingly more useful variables, and then to reconstruct finer details of the input data samples. What's important to note is that besides reconstructing the input data, after training, the latent space can be sampled to generate new data samples. In this animation, I show how the generation of new data samples can be performed with this model. On the left, you can see a bidimensional representation of the latent space with 4 numbers which identify the position in the latent space of 4 selected designs. The combination of variables representing these designs are linearly interpolated in the latent space and to produce new combination of variables. These are then fed into the decoder to generate new data, which are not part of the initial dataset. In this second application, the input is not given in the form of variables, but as another image, which represents a potential design footprint. The objective of the model this time is to interpret the main visual features in this bidimensional abstract image and to generate a design which is consistent with the knowledge it has acquired during training. This application demonstrates that the model is able to interpret information provided in a different form of representation, and it's also able to generate solutions which are considerably different from what it has been shown during the training process. This slide, I want to point out that although the model can deal only with 2-dimensional image, it's pretty straightforward to convert a depth map back into a 3D model, and this conversion process can be performed easily with any CAD software. So as final remarks, I want to stress a few points. The first is that variational encoder can potentially offer an alternative for the construction of design space, and this can help designers during the conceptual stages of the design process where considerations about performance are more relaxed. And a variational encoder constructed design space can be also explored with traditional optimization techniques by imposing some performance criteria. And finally, for this application, I've just tested the model on an artificial dataset, which was constructed through a parametric model, but I've already successfully tested the same approach on a dataset of real shells and spatial structures. And these results will be presented at the IWSS2020 conference. Thank you all for listening.
Thank you very much, Gabriele. And is there any question? I see in the chat one maybe from Francesco Marmo. Or,
yes, I just wish to connect to the last slide of Gabriele. And I wonder if they tried conventional optimization techniques and how are the performance of those techniques compared with their proposals.
I haven't tried it yet because the main point of this test was testing the ability of this model to actually extract meaningful design variables from a dataset of precedents. What's important to note is that dataset that I've used of course, has some variables embedded in the shapes because it was generated through a parametric model. But the model has no knowledge whatsoever about these variables. And besides that, it was able to reconstruct some important feature. For example, here I'm showing to the model just an abstract image. I'm not giving any information about supports, nodes, or shape of the openings or whatever. But the model is placing support edges along some visual features, which in this case are recognized in the corners of the shape. So for me, this application was important to test if the model is actually able to extract visual features from a dataset of precedence. And of course, this dataset is really simple, but I'm going to show you I will show at the IWSS conference how using a dataset of real shells and spatial structures will produce much more complex results.
Okay, thank you.
Okay, thank you very much. There is also Stefano Gabriele. We have time. We are a little late, but I think it's good. We have 1 minute for another question.
It's very interesting, especially for people like me that works as engineers in the departments of architecture. Even if I don't know how much architects could be in agree with this kind of approaches. Sometimes I'm not saying that it's, but what is it? Could you speak a little bit more about the parametric choices that you made? So which kind of family of surfaces, or they are all taken from a dynamic relaxation approach, or you also have parametric families of surfaces that has some particular behavior with respect to, for instance, some kind of loads?
No, all the shapes that I've generated to construct the dataset were created through a dynamic relaxation algorithm. And this was just to have a consistency, because this kind of models can even deal with different structural topologies. And that's again what I've done for the next stage of this research. No, the only shapes that I've generated for the dataset constructions were funicular shapes generated with a dynamic relaxation algorithm. And I haven't tested the actual structural performance of them.
Thank you.
Thank you very much, Gabriele, again for your presentation. And so this was our last speaker for the morning, the first morning session. I thank all the speakers and all of you for staying here. And then we start after the short break at 11:10, and the connection will be going on, so the speakers can check if everything is fine during the break. Thank you very much again, and then we see you later. Thank you. Thanks to all the speakers.
Yes.
Okay.
Andrea, I want just to recall that we are going on a YouTube live now that we will interrupt. We will start again at 11:10, and people that is viewing the workshop on YouTube, they have to check the IWSS channel or the website to be notified for the next live broadcast. So thank you, everyone.
Thank you, Francesco. Okay. So I will just mute my microphone and go drink a coffee.
I would like to say hello to Alberto Pugnale. Hi, Alberto.
Hello. Sorry, we haven't said hi before. Thanks for accepting our contribution. And also hi to Attilio and all the friends from Italy.
Ciao, Alberto.
Ciao.
So Amedeo, maybe you can stop the live.
Okay,
for the break.
Yeah.